All right, welcome everyone. Let's get started for today. So first of all, just a reminder, if you have Thursday recitation, you have your recitation exam 5 today. No homework due tonight, but we do have some homework due next Tuesday and next Thursday. So just keep that in mind for your homework assignments. And um, so today we're going to be we're going to finish up optimization, and we're going to move into our kind of our last major topic for the course, which is going to be integration. So let's finish up with our last example here for optimization. And this is an applied optimization problem where we're going to have some constraint to it. All right, so let's read through the problem first. We want to find the point on the parabola y squared equal to 2x that is closest to the point 1 comma 4. So we're going to kind of go through the process of solving these applied optimization problems. And really the step to get you started is to draw a diagram and just thinking about what variables you're going to use and what possible equations that you might have to work with. So our first step here kind of has already been done. We have our diagram already kind of drawn out. But if it wasn't there, you'd have to draw the parabola and plot the point for yourself. So we have the point 1 comma 4. And what we're interested in here is figuring out which point on that parabola is closest to the point 1 comma 4. So if we have some point x comma y that's on our parabola, what we're interested in is the distance between that point and the point 1 comma 4. So that's really what we're interested in. So, to get kind of these optimization problems going, you want to draw in a diagram and introduce the variables. And so the variables here are just the coordinates of our kind of arbitrary point at this stage, x comma y. So we want to then identify what we called the objective equation and the constraint. And so the objective equation, this is the thing that we're trying to optimize. We want to find the largest or the smallest. And so in this case, we're looking for that wording that's indicating some sort of maximal or minimal quantity. And what we're seeing here is the word closest. So the way that we measure whether how close together 2 points are is with distance. And so that's really what we're trying to determine here is the distance between the point 1 comma 4 and some point x comma y on our parabola. So that's going to be our objective equation. And the way you calculate distance, there's a nice distance formula. It's equal to the square root. You subtract the x coordinates, so x minus 1 of our 2 points. So the first x value here comes from just our arbitrary x, and then the 1 comes from the 1 in our other point, 1 comma 4. So we subtract the x coordinates and square it, and then we add to that the difference of the y values, the y coordinates. So we do y minus 4 squared. And all of that's underneath our square root function. So that's just the distance formula for the distance between 2 points. All right, so what is our constraint? So our constraint, this is the formula or the equation that puts some restriction on our variables. And the restriction that we're seeing here is that whatever point we use, in this case x comma y, it has to be on the parabola. And as we go through this example, if you have any questions, feel free to let me know in the chat. So as we look at this parabola, any point that we pick, it has to fall on that parabola. So the variables x and y, whatever they're going to be when we maximize or minimize this distance function, whatever variables we pick, they have to satisfy that equation for the parabola. So our constraint equation is this y squared equal to 2x. So no matter what we pick for x and y, ultimately, it has to satisfy that constraint. They has to be on the parabola. All right, so that's really the first step. Just identify the two equations that you're going to be working with. So then in step 2, we're going to solve our constraint equation for either variable. So you have some choice, so pick which one's easier. In this case, it's easier to solve for x. So if we divide both sides by 2, we get x is equal to 1/2 y squared. And then we're going to plug that into our objective. So we're going to take that, and in our objective function there, wherever we see an x, we're going to change it to 1/2 y squared. And what this does for us is it gives us a one variable function then. So we end up with this objective function d is equal to the square root of 1/2 y squared minus 1 squared plus y minus 4 squared. And that's just a one variable function. So all the techniques that we've learned in a lot of the previous sections of finding the critical points and setting the derivative equal to 0 and testing our critical points, all those optimization techniques that we've learned, we can actually do that now for this one variable function. But before we get there, we're actually going to kind of simplify our work down a little bit. So we're going to modify this function just a little bit in order to make our derivative and solving our derivative when we set it equal to 0, we're going to simplify that down a little bit by just modifying what we look at. So this is going to be step 4. And normally we would want to optimize just that one variable function as is. So let's just write it down again. But what we're going to do instead is we're going to look at the term underneath the square root. So if we look at this, we're just going to consider those terms underneath the square root. And we'll just give those a name. Let's call it f of y. So it's going to be a function. It's the inner function. It's underneath the square root there. So we're just going to look at our function without that square root. So why do we want to do that? Well, if we were going to differentiate the square root function, we'd have to use chain rule. We'd end up with a fraction, so we'd end up with a negative exponent. And then there's going to be a lot more. The derivative is just going to be more complicated, and it's going to be more complicated to solve. So if we look at just the inner function, there's going to be a little bit of work doing the derivative, but it's not going to be as nasty as if we had left the square root function in. So what we're ultimately going to do is we're going to optimize this simpler function. And the reason why we can do that is what we're going to discuss here. So let's suppose we go through the optimization process and we figure out the y value, we'll call it ym, that minimizes this revised function. So suppose we just consider this easier function, this simpler function, and we figure out the y value that minimizes it. So ym, what does that mean? Well, it means that when we plug ym into this inner function, it's smaller than all of the other values of our function. So it's the smallest value of our function. That's what it means to be minimal. So this is true for all y. So let's suppose that we figured out which y value gives us the minimum of this inner function little f. Well, now let's suppose that we were to then apply the square root to both sides of that inequality. The square root function actually behaves nicely with inequalities. So since the square root function is an increasing function, we can apply it to both sides of an inequality, and it preserves the direction of the inequality. So it preserves the inequality. So we found this value ym that gives us the smallest value of function f. If we apply the square root to it, well, the square root preserves that inequality. So the square root of f of ym must be less than or equal to the square root of f of y for all y. And the function square root f is just precisely our distance function that we had from above. So note, our original distance function is just the square root of function f. So this must be our distance function evaluated at ym. And this, on the other side of our inequality, this is just our distance function evaluated at any y value. And since the square root preserves the inequality, that inequality must be true as well. So the distance function evaluated at ym must be less than or equal to the distance function evaluated for any y value. And that's precisely what it means to be the minimum. So this last inequality here shows that ym also minimizes our distance function dy. So when you're dealing with a square root, if you can minimize the inner function, well, then that same x or y value also has to minimize the entire composite function, the entire square root function. So we can just consider the inner function and figure out the y value for where just that inner function is the smallest. And that's what we're going to do next. So we're just going to minimize that inner function f of y instead. It's just going to make the calculus just a little bit easier. Not necessary, but it's something that we can do to make it a little bit easier on ourselves. So let's try that out. We're going to continue on with step 4, the optimization process. But now we're going to optimize just that inner function without the square root. So the 1/2 y squared minus 1 squared plus y minus 4 squared. And so how do we optimize this function? Well, we find the critical numbers, we test the critical numbers, and then that's basically it. So we want our critical numbers, so that means we need to do f prime. So we're going to do the derivative. So when we differentiate that first term, we bring down the 2, keep what's inside the parentheses exactly the same, and then we subtract 1 from the exponent, And then we multiply by the derivative of the inner function. So derivative of 1/2 y squared minus 1. So that's general power rule. Then we do the same thing for the second power function, that y minus 4 squared. When we differentiate that, bring down the 2, keep what we have in the parentheses exactly the same, and then multiply by the derivative of what's inside. So the derivative of y minus 4. Keep differentiating, and we'll simplify as we go. So the 2, if we distribute the 2 there, we end up with y squared minus 2. And then differentiating the 1/2 y squared minus 1, we end up with just y. And then we'll distribute that other 2, so we get 2y minus 8. And then the derivative of y minus 4 is just 1, so we won't write the multiplication by 1. And we just clean this up a little bit more. We distribute the y here to the y squared into the 2. And if we do that, we would see we'd get y cubed minus 2y. Then we have plus 2y. So those are going to cancel. And then we have minus 8. So we end up with y cubed minus 8 as our derivative. Then we want to figure out where the derivative is 0. So we set our derivative equal to 0. And when we solve that, we get y is equal to the cube root of 8. And for cube roots, there's no plus or minus. So it's just whatever the sign is. So in this case, 2. So we end up with y equals 2 there. If it was a square root or an even root, then you do the plus minus. But if it's an odd root, there's no plus minus. It's just whatever the sign is. And then we would also want to look at for where the derivative is undefined. But our derivative is just y cubed minus 8. There's no division by 0. There's no square roots there. There's no natural logs. So there's no issue. So no place where our derivative here is undefined. So we found only one critical number. So we want to test it then. And that's part B. We want to test it. And normally the second derivative test is a little bit quicker. So that's what we're going to try first. Sometimes you get an inconclusive, and that's okay. Then you just have to go back and do the first derivative test. But let's see what we get when we do the second derivative test here. So that means we need to calculate our second derivative. So we're looking at our first derivative, which was y cubed minus 8, and we're just going to differentiate that. So derivative of y cubed is 3y squared. And then the derivative of the minus 8 there is just 0. So that's our second derivative. Then we plug our critical number in. So when we plug 2 in, we get 3 times 2 squared. And we really don't care about the actual number. We just care about whether it's positive or negative. So this one we can actually do the arithmetic. It ends up being positive 12. But you could also just consider the fact that the 3 in front is positive, and then when we square anything, that's going to be positive as well. So if they were sort of bigger numbers, you could just kind of use that sort of argument to say that the result is positive or negative. But in this case, we can do the arithmetic. We end up with positive 12. So when our second derivative is positive, it means the shape there must be concave up. And to help us remember what the second derivative test says, let's draw in a concave up shape. And we see that we have a local minimum. At y equals 2. But not only is it the local minimum, we found only one critical number. So we can actually say a little bit more. It's the absolute minimum. So one critical number gives us a little bit more information there. All right, so we figured out the y value that gives us, well, we figured out the critical number, and then we showed that that critical number does give us the minimum. The last step then is to just make sure we go back and actually answer the question. And so if we read back into our problem here, it says find the point. So it doesn't say find the y value, it says find the point. So we need to find both x and y. So we just want to make sure we find everything that the problem is asking for. So we want to find the actual coordinates of our point. And we know that the y coordinate is 2. So we want to figure out the x coordinate. And this is where our constraint equation comes back into play. So we know our constraint equation is that y squared equal to 2x. We already kind of solved in some respect. We solved the constraint equation for x. So we knew that x was equal to y squared over 2. So let's just plug our y value into that. And we get x is equal to 4 over 2, or just 2. So the actual point is 2, 2. And if we go back to our, that's it. We've really answered it at that point. So we figured out the point, and we also justified that it is the smallest. So this step of justifying here, this is important. So we will be looking for that on the homework, on the exam questions. We want to see that you can justify that this is giving you either the minimum or the maximum value. There's not really going to be any trick questions where the problem says find the minimum, and if you do the second derivative test, you get a maximum. We won't really give any trick questions like that, but we do want to see that you can actually use one of those derivative tests to justify that it is a minimum or a maximum. And if we go back to our graph here, it's kind of what you would expect. So what is the point that we found? Well, it was the point actually right here, 2, 2. And so I'm sure there's a geometric argument that you could have done to figure out that point. So you maybe could have looked at, done some sort of like right angle. This is a right angle here, and figured out the slope. But what we're doing here is more in the context of an optimization, using calculus to figure out instead of geometry. All right, so that'll be kind of the last example we do for optimization. And we're going to move into learning outcome I1. So here, we're going to learn how to calculate the indefinite integral of basic functions. So what are basic what do we consider basic functions? Well, these are ultimately going to be integrals that we can solve by using either the sum, difference, or constant multiple rules in conjunction with our list of, we'll have a nice list of some elementary forms, just like we had for derivatives. So this is going to feel very similar to the derivative lecture, in the context of, here's a table, let's refer back to the table and all of that. So first, let's start with some definitions, though, and kind of our motivating question. So the motivating question here is, let's suppose that we have function f of x. And we learned all those differentiation rules, product rule, quotient rule, chain rule. We learned all those derivative rules that allowed us to differentiate. So we could go from f of x to f prime of x. We learned all those techniques. And so the motivating question for this section here is, what if we started with the derivative? Could we go backwards? So if we started with f prime, is it possible to recover the original function f of x? And so the answer is almost satisfying. It's not quite, but we can get pretty close. So we can do pretty well, but we can't quite recover the exact original function, and we'll see why in a little bit. But we're going to call this process of going backwards anti-differentiation. Or indefinite integration. And I'm just looking here. I want to change the word here to differentiation. So going from f to f prime is differentiation, and what we're going to call going from f prime back to f, we'll call it anti-differentiation, or, spelling today, indefinite integration. And so we're going to really think of these as these processes that we're going to consider. We're going to consider these as really reverse operations. So differentiation, we see, is going to undo anti-differentiation, and anti-differentiation, for the most part, will undo differentiation. But first, let's start with the definition. So we say a function capital F is an antiderivative of function little f if the derivative of capital F is equal to little f. So it seems like a simple definition, but it's a lot of function notation going on. So it's better to consider this with an example. So let's look at the function x squared, and we'll call that little f. We're going to show that the function capital F1, which we'll say is 1/3 x cubed, we'll show that 1/3 x cubed is an antiderivative of little f. So how do we do this? Well, we're just going to take f1 and we're going to differentiate it. So if we differentiate 1/3 x cubed, we'll show our work here. We don't normally show all this though anymore. So we're just differentiating the x cubed. We have a constant multiple in front, so we end up with 1/3 times 3x squared, and then the 3 and the 1/3 cancel, so we're left with x squared. And that's precisely, for this little example, that's precisely lowercase f. So what we've shown, just in this little calculation, is that the derivative of f1 is equal to little f. And that's what it means to be an antiderivative. So 1/3 x cubed is an antiderivative of x squared. So that checks out. Let's try it again for a slightly different function. We'll call it capital F2, and this is 1/3 x cubed plus 1. And we'll show that that's an antiderivative of lowercase f. How do we do it? Well, we're just going to differentiate this supposed antiderivative and see what we get. So let's differentiate 1/3 x cubed. And we know that that derivative is 3x squared, and then the derivative of 1 is just 0. And simplifying this, we end up with x squared, which is just little f of x again. So this calculation is showing that capital F2 prime is equal to little f. And that's precisely what it means for capital F2 to be an antiderivative of little f. And so what we're seeing here is we have two different functions, 1/3 x cubed and 1/3 x cubed plus 1, that are both antiderivatives of the function x squared. And so we're just going to make note of this. A function can have more than one antiderivative. And as we're going to see, it actually has an infinite number of distinct antiderivatives. So, but they all differ by a constant. And that's the main result here. So any two antiderivatives differ only by a constant. So more exactly, suppose we have capital F1 of x and capital F2 of x, and they're two different antiderivatives of the same continuous function little f. Well, then capital F1 is equal to capital F2. It's almost equal, but it's different by a constant. So capital F1 is equal to capital F2 plus c. Some constant c. We don't necessarily know what it is, but they differ by a constant. All right. So what does this plus c really mean that we're adding on for our antiderivatives? So we have antiderivatives. What does this plus c really mean? So let's look at two graphs. Here on the graph on the left, we have our two antiderivatives of x squared. So this one is the 1/3 x cubed. And then this one over here is the F2. This was the 1/3 x cubed plus 1. And we're going to kind of consider those two antiderivatives in the context of two parallel lines. So, unrelated, but in the graph to the right there, we have two parallel lines. And there's going to be some similarities between these two. So the one thing we notice is that when we look at these two graphs, each, whether it's the two antiderivatives that we saw or the two parallel lines, they're just vertical translations of each other. And this is really what the plus c is doing, is it's just moving our graph up or down. So when we have two distinct antiderivatives, they're almost the same, they're just vertical translations of each other. And that's what we see here. So what does it mean to be a vertical translation? Well, for our little example here, if we were to pick any two corresponding points, the distance between those 2 points is always going to be constant. So there's, for this particular little example, we have a distance of 1 unit between corresponding points. So let's look for parallel lines. Let's pick 2 corresponding points. So 1 on each line, and the distance between those 2 points is 1. What about these 2 corresponding points? Well, the distance between those 2 points is also 1. And maybe one more. Maybe these 2 points. What's the distance between those 2 points? Well, in this case, the distance is 1. So for those 2 parallel lines, if you pick any 2 corresponding points on those lines, the distance between them is 1. Now for the context of our antiderivatives, same kind of deal. you pick any two corresponding points, and the distance between those 2 points is 1. So whether we pick the corresponding points there at x equals 0, or maybe we pick the corresponding points at x equals 1, or maybe we do something like -1/2, the distance between those two corresponding points is always 1 in this case. So our two antiderivatives, they differ by a constant. We've just moved one up or the other one down, however you want to think about it. So they're just vertical translations. Another thing to kind of consider is that if we were to look at these two graphs, they have the same slope at each x value. So for the parallel lines, that really shouldn't be too surprising. Two parallel lines don't intersect, and for regular geometry, two parallel lines have the same slope. So that's not too surprising. But what's a little bit more surprising is for our two antiderivatives, if you pick any two corresponding points on those two graphs, they have the exact same slope. So for instance, if I were to pick this point at x equals 0 here, it looks like the graph flattens out. So it looks like I have a slope of 0. And if I were to pick that same corresponding point on the other graph, it flattens out at the exact same place. So it looks like we'd have a slope of 0 there as well. And so for those two antiderivatives of x squared, any two corresponding points are going to have, the graph is going to have the same slope. And really, why does that happen? Well, if we were to consider the slope of f2, the slope of f1, what is the slope of f1? Well, that's just f1 prime. It's just the derivative. And if we were to consider the slope of f2, the other one, well, what's the slope of f2? That's just f2 prime, just the derivative. And we know that the derivative of each of those is equal to x squared. It's equal to what we were calling little f. So the slope of f1 is always going to be equal to the slope of f2, no matter where you go on those curves. So really, we could think of antiderivatives, distinct antiderivatives, that plus c constant is really just moving our graph up and down, and it preserves the slope of our graph at every single x value. And so we want to give a special name and give some special notation to this. So usually when we talk about antiderivatives, we use the notation for indefinite integrals. So suppose that little f of x is a function whose antiderivatives are capital F of x plus c. And so what we write is the integral of little f of x dx is equal to capital F of x plus c. And so just a little bit of discussion here about the notation. This is an integral sign. We call this an integral sign. And it looks just like if you wrote an S, I'm probably doing that backwards, and then you stretched it out. So it's just like a really stretched out S. The dx here, that's important. That's our differential. And then the function inside here, we call that, well, it's little f of x, but we give it a special name. We call that the integrand. So it's the thing that we're actually finding the antiderivative of. So when we see this sort of notation, we want to think of it almost like directions, instructions telling us to find the antiderivative. So when we write integral sign and then some stuff in between the integral sign and dx, really what that means is figure out the antiderivative of everything in between the integral sign and the dx. So it means just find the antiderivative. And this is very similar to the notation we saw for derivatives. Normally, we would write something like d dx with some brackets, and that just means find the derivative of everything inside the brackets. So this is just notation really saying find the antiderivative or find the indefinite integral. And we want to kind of really keep in mind that differentiation and integration, or antidifferentiation, they're almost reversed operations, reverse processes. So to see that, let's say that we start with some function little f. Let's say we start with little f of x. If we were to integrate that function, we would get the integral of little f of x. So that's some new function. And let's take that function and differentiate it. And what we would get out is we would get back exactly where we started. We would go back to little f of x. So if we start with a function and then we integrate it and then differentiate that, we're back to where we started. So it really is kind of behaving like a reverse operation. It's undoing what derivative does. Now let's kind of go in the opposite order. Let's say we start with a function capital F of x, and let's say we were to differentiate that. We would get the derivative of capital F, so maybe like f prime. And let's say we wanted to then integrate that. So we start with a function capital F, we differentiate it, and then we integrate the derivative. We could think of the integral sign and the derivative as almost canceling out. And what we get out here, we get out capital F of x, but not quite. We have a plus c here. And so, these are really almost reverse operations. So that's the right context to think about this. But almost. And so why is it not quite? Well, differentiation kind of destroys a little bit of information about our function. So every time you do the derivative, you lose a little bit. And we know that because when we differentiate a constant, derivative of a constant is 0. So you're kind of losing that information. Each time you do the derivative, you've lost that information. And so it's not quite possible to fully recover that. And that's what we're seeing here with this plus c, is we've lost a little bit of information by doing the derivative first. And that's okay. It's just what happens. But that's just what happens with differentiation. We lose a little bit of information. So that's why we have plus c instead of just the exact function. All right, so that's sort of the build-up here. Let's actually go through, the rules on how to actually kind of calculate an antiderivative. And so just like for derivatives, we had a whole bunch of rules. Doing antiderivatives or doing integration, we're going to have a whole bunch more rules. And that's what we're going to kind of just start talking about next. So first, what happens when we integrate a constant? So k here is a constant. Well, what we get is kx, k times x, plus capital C. So this one's really telling us how to integrate a constant function. So we don't see any variable there. We're just integrating everything inside the integral sign and the dx. So it's just a constant by itself, unattached to a variable. So normally when we do derivatives kind of, you're subtracting powers of x. Integration kind of builds them back up. And that's what we can see with our integration version of the power rule. So suppose we want to integrate the power function x raised to the power r. How this works, well, let's read through the formula. It's 1 over r plus 1 times x raised to the r plus 1. And so derivatives, for differentiation, the power rule was we subtract 1 from the exponent. With integration, we're kind of doing the opposite. So we want to add 1 back into the exponent. So when you do integration, you should end up with, you should be putting more variables in. So you're kind of building your function back up. Differentiation is kind of taking variables away. It's kind of the feeling when you do these. So our integration version of the power rule, we're adding exponents back in. So let's kind of see how this power rule works. So our first step is to keep the variable the same. You could just remember the formula, but I find it easier to think of it as just a process, a thing you do. So we keep our variable the same. So x. For integrating x to the power r, we keep the variable the same, x. Then the next step, step 2, is to add 1 to the exponent, to the old exponent. So our old exponent was r, we add 1 to it. So that's step 2. And then the third step is to take that old or that new exponent and flip it and put the reciprocal in front. So 1 over r plus 1. That's the last step for doing this power rule. So we multiply by the reciprocal of the new exponent. So when I do this, I kind of go in that order. Write down the variable, add 1 to the exponent, and then once I have that new exponent, then I put the constant in front. Now there is a word of warning here about our power rule, and this only works for r not equal to -1. So if r is -1, we have a separate rule for that, which we'll see in a little bit. But if you were to try and go through the power rule, you would see that it's not going to work because you would end up with like division by 0, and that should be a warning sign. So if we have that -1 exponent, we're going to want to write that as 1 over x. And the integral of 1 over x is going to be something different. It's going to be something special. So it'll involve log functions. So we'll keep that in mind. So the power rule almost always works. The only kind of special case there is when the exponent is -1. All right, so let's try some examples. So let's find the most general antiderivative of each of these functions. So for part A, we have the constant function 5. So really what we want to do is just figure out the antiderivative of the constant function 5. So this is just a constant that's by itself. So what do? Well, we just multiply it by our variable. So 5 times x and then we add in our plus c at the end. So adding in the plus c will always be something we do the very last. So just 5x plus c here. All right, so let's try the next one, part B, where we're going to find the general antiderivative of x cubed. So here we want to do the integral of x cubed. And this is where power rule is going to come in. So this is just a power function. Our variable is x, so we start by just writing our variable down. It's x. We add 1 to the exponent, so that takes us up to 4. And then we take that new exponent and flip it and put it in front, so 1 over 4. So we get 1 over 4 times x to the power 4, and then we add in our plus c at the end. So again, where does this new exponent come from? Well, it comes from our old exponent, which was 3. We add 1, and that gives us 4. All right, so what about part C here? We want to find the general antiderivative of square root x. So that means we want to integrate square root x. And just like for derivatives, we usually want to rewrite root functions with an actual exponent. So that's what we're going to do. We're going to rewrite the nth root as raised to the power 1 over n. So instead of square root x, we're going to do x to the 1/2. And now we're going to do power rule. So our variable is x. Leave a little bit of space there. Our variable is x. We add 1 to the exponent. So 1/2 plus 1 is 3/2. And again, where does that come from? Well, our old exponent was 1/2. We add 1, get a common denominator if you need to, and then we end up with 3 over 2. So our new exponent is 3/2. And then we take that fraction and we flip it, put it in front. So 2/3. So our antiderivative is 2/3 times x to the 3/2. And then we want the most general antiderivative, so plus c. So we add on our plus c at the end. All right, last one. We want to do the general antiderivative of 1 over x squared. So that means we want to integrate 1 over x squared. And just like for derivatives, when we have a fraction like this, we want to try to rewrite it, if possible, with a negative exponent. And that's what we're going to do. We're going to rewrite this as a negative exponent. So instead of 1 over x squared, we're going to do x to the negative 2. And negative 2 is perfectly fine. So someone had a question for a power rule. The power rule just doesn't work only if that exponent is negative 1. If it's any other negative, power rule works. So the negative 2 here, we can still do the power rule. Power rule will work just fine. So that's a good question. So power rule still works for r equals negative 2. And let's apply it. So we write down our variable. We add 1 to the exponent. So we go from negative 2, we go up to negative 1. Then we take that new exponent, flip it, put it in front. And then we add our plus c at the end. And then 1 over negative 1 is just negative 1. So just a negative. So if we wanted to, we could write this as negative x to the minus 1 plus c. Or if we want to go a little bit further and write it back as a fraction, we could do that as well. So we could write this as negative 1 over x plus c. All right, so just a little bit of practice there using our power rule. Now we have some additional rules that kind of expand what we can do the antiderivative of. So first we have a constant multiple rule. So this tells us what happens when we have a variable times a constant. And what we can do is, we can move the constant k . outside the integral sign. And we had a very similar rule for derivatives. We could, instead of having that constant multiple in front and worrying about it, we could just sort of say, all right, let's move it outside of our focus here and just focus on differentiating the variable part. So same thing for integration. Let's get the constant out of there and just focus in on integrating the variable part. So that's the constant multiple rule. One thing to note, so you might be tempted at some point and you can't do it, is that you can't move variables outside of the integral. So let's say we had x times x squared. We can't move any of those x's outside the integration. So they all have to stay inside the integral sign. So we can't say take this x and put it in front. So all the variables are kind of stuck inside the integration there. So it doesn't equal can't move any of those variables outside. Doesn't work. Only constant terms. And it has to be a constant multiple. So if we're adding a constant that's by itself, that's a different story. This is only for a constant times a variable. And then we also have our sum rule, which also works if we had negatives. So if we had subtraction here. So basically the same rule. Sum, difference, however you want to call it. So if we have the integral of a function f plus a function g or minus, it's the integral of function f plus or minus the integral of function g. So really we can think of this as we can split up the integration wherever we have a plus or a minus sign. So wherever we have addition or subtraction, we can split up our integration. And so taking these two kind of rules together will give us a technique which we'll use, and we did something very similar when it came to differentiation. We're going to call it term-by-term integration. And we'll see that in the examples coming up. So let's see how first the constant multiple rule works. So let's look at part A here, which we want to do the integral of 2 times x to the power 5. And we see that it's a constant term times a variable. So it's a constant multiple. So the way the constant multiple rule works is we can bring that 2 out in front of the integration. And just worry about getting the antiderivative of x to the power 5. And that's what we can do. Let's get the antiderivative of x to the power 5. It's just x to the power 6, and then we take that new exponent, flip it, put it in front. So 1 over 6. So we end up with 2 times the antiderivative of x to the 5. So 2 times 1 over 6 times x to the power 6. We add in our plus c at the very end, and then simplify as needed. So 2 times 1 over 6 is 1/3. So there's our antiderivative. Now let's try the integral of 4 over x cubed dx. And the goal is when you have a term like this, where it's a constant and a variable, you want to try to rewrite it in this format, where a is a constant. You want to try to separate your terms. So you want your constant in front, and you want your variable part to the other side. So you just want to try to keep things separated there. So for this 4 over x cubed, let's try to separate it and write it in that format. So the first thing we could do, and this is the same kind of thing we would do for differentiation. So we've been doing this all along, but just let's see how it looks for integration. So we might write this as 4 times 1 over x cubed. And then, so we've just taken the 4 off the numerator, kind of separated it that way. And then for 1 over x cubed, we know what to do with that. We want to rewrite that with a negative exponent. So 4 times x to the negative 3. And now that's a good format. It's a constant times a variable. So now we apply the actual rule, which says we can move the 4 out front. And then we can just do the antiderivative of x to the minus 3. So we apply the power rule there. Our variable is x. We add 1 to the exponent, which bumps us up to negative 2. We take that new exponent, we flip it, and we put that in front of the x. We get negative 1/2 in the front there. We add on the c at the very end. And then we simplify as needed. So we have a 4 times a negative 1/2. We can clean that up and write it as negative 2x to the negative 2 plus c. And there's our antiderivative. Now when we're, once we get the hang of these, just like for derivatives, we don't really show the constant multiple rule step or the sum rule step. So for instance, normally when we're doing these, we wouldn't show our work for this step right here. Same thing for the first one we did. We wouldn't really show that step. So once you get the hang of these, you're not going to be showing that on a regular basis. All right, so let's try one more, this time not showing that step. So for part C, we have 5 times the cube root of x. Let's go through our normal strategy first of just rewriting that as a power function. So this would be 5 times x raised to the 1/3 power. So we have it in that format now of a constant times a variable. And what would we normally do? Well, we just really focus our attention on that variable part. So we would have 5 times whatever the antiderivative of x to the 1/3 is. So the antiderivative of x to the 1/3, our variable is x. We add 1 to the exponent, which bumps us up to 4/3. We take that new exponent, flip it, and put the reciprocal in front. So 3/4 in front. And in case you can't quite see where this new exponent comes from, our old exponent was 1/3. We add 1 to that. And if you need to, you could think of a common denominator, 3/3, which is 4/3. And then once we're done with all the integration, we put our plus c at the very end, and then we simplify. So we could do the 5 times 3/4, and that would give us 15/4 x to the 4/3 plus c. So there's our antiderivative. So that's about, for part C there, that's about a realistic level of work that you would show. Minus this. You're probably not showing the fractions, and that's fine. All right, let's try another example. This time we're going to use the sum rule. So we're going to do the integral of 2x to the power 7 plus 6x plus 5. And so what the sum rule and the difference rule really say is we can split up the integration wherever we see a plus sign or a minus. So that's the first thing we're going to do, is we're just going to split this integral up into 3 separate integrals. So we'll have the integral of 2x to the power 7 dx plus the integral of 6x dx plus the integral of 5 dx. So just be careful with notation. each integral should have an integral sign in front and a dx at the end. So just want to get into the habit of good notation here. And that differential, we're gonna see that actually becomes very important in a lot of the later work for the unit we're going to be talking about in the upcoming weeks. And then in Calc 2, differentials become very important. And then in Calc 3, even more important. So it might seem insignificant now, this dx that we write at the end, but we want to get into good habits of always including that when we're talking about integrals. So that's something, for exams and for homework, that's something we're going to be looking for. Are you correctly using differentials, the dx, in your work? All right, so we've split up our integral into 3 separate integrals. And this is really the sum difference rule that allows us to do that. Then let's just see the constant multiple rule in action again. So for that first one, we can bring the 2 in front. For that second one, we can bring the 6 in front. And for that last one, it's just the integral of an unattached constant, so we'll just leave that as the integral of 5. We're not going to bring the 5 out in front. I mean, we could, but we'll just leave it in there. So this step is our constant multiple rule. We use that rule twice. Move the 2 out and move the 6 out. Now we go through, we just have the integral of some different power functions and then a constant. So now we go through and do the integration. So what's the antiderivative of x to the power 7? Well, it's x to the power 8, and then we put the reciprocal in front, so 1 over 8. Then we have plus 6, and then we're doing the antiderivative of x. So we add 1 to the exponent, bumps us up to 2. Take that new exponent, flip it, put it in front of the x, 1/2. So we get 6 times 1/2 x squared. And if you're not seeing how we got that, when we write x, there's sort of a hidden exponent there of 1. And then finally, for that last one, it's just a constant that's by itself, not attached to any variable. So how do we integrate an unattached constant? We just slap on a variable, so 5x. And then the very last thing we do is just one big plus c at the very end there. So there's our antiderivative. And might want to simplify it down a little bit. So 2 times 1 over 8 is 1/4. X to the 8. 6 times 1/2 is 3. So 3x squared plus 5x plus c. And so we just put 1 plus c term there at the very end, just to make it easy. Technically each of those separate integrals would have its own constant, but we could just combine all those into one big constant, and that's fine. All right. So that's doing the integral, showing all of our work, our sum difference rule and our constant multiple rule. But once you get the hang of these, you're not going to be showing all of this. So realistically, what is the amount of work that I would be expecting for you to show for something like this? And we'll use that to illustrate our technique of really term-by-term integration. So when we look at an integral, we just want to identify each of the distinct terms. And those are really the things that are separated by addition or subtraction. So when I look at this integral, the one we just did, I'm really seeing 3 terms. I see the 2x to the 7, I see the 6x, and then I see that plus 5 at the end. So when we look at each of those terms, we want to write them in the form a times x to the power r. We want to write them as a constant multiple. And so when we go through and do the integration, it helps to kind of just circle the variable parts, go term by term, and circle just the variable parts. So x to the 7, x, and then there's no variable part, so we'll just circle the constant part in that last term. And we're going to go through and we'll keep the structure exactly as is. So it'll be 2 times whatever the antiderivative of x to the 7 is, plus 6 times whatever the antiderivative of x is, plus whatever the integral of 5 is, and then we'll put our plus c at the very end. And then you just go term by term, and you just do the antiderivative of each of those variable parts. So what's the antiderivative of x to the power 7? Well, it's x to the power 8, and then you put 1 over 8 in front. Then you go to the next one. What's the antiderivative of just the x? Well, it's x raised to the power 2 with a 1/2 in front. And then you go to that last term. What's the antiderivative of 5? And the antiderivative of 5 is 5 times x. So you really just go term by term, and you integrate as needed. And so the structure is preserved. So it's 2 times the antiderivative of x to the 7 plus 6 times the antiderivative. So wherever you had originally had a plus, that's going to carry on. Wherever originally you had a multiple, constant multiple, that constant multiple is going to stick around. And then you would simplify. So once you have all the antiderivatives, you simplify. So you're just keeping any original addition or subtraction signs that you see. Those are preserved when you do the integration. So really, that's the amount of work you're doing. So a lot of these, you probably just do it and you write down the answer and you're done. For the next one, you might need to show a little bit of work. So we want to write these in the form, when we look at this, I see 2 terms. I see the first term, and then I see a subtraction, and then my second term. So we're looking at 2 terms here. And we want to write each of those in the form constant times an x term. So that 5 times x to the 4, that's good, but it's that 4 over x cubed, which we might need to do a little bit of work with before we can integrate it. And that's really where our work is going to come here, is by just writing that as 4 times x to the 1/3 power, or to the negative 3 power. So the 4 is just a constant multiple. It's not being affected by that exponent. It's just multiplication here. And now we've got it in the correct format for actually doing the integration. So again, we have the first term, the second term, and we're subtracting. So when we do this, the 5 is a constant multiple. Then we'll get the antiderivative of x to the 4. Then we have minus 4. 4 is a constant multiple, so it sticks around. And then we'll do the antiderivative of x to the minus 3. And I'm going to need a little bit of more room, so let me... And then we have our plus c at the end. And let's get our antiderivatives. So x to the 4th, our variable is x. We add 1 to the exponent, put the reciprocal in front. So 1 over 5 times x to the 5. Then for the other x term, it's x. Let's add 1 to the exponent, which bumps us up to negative 2. Take that negative 2, do the reciprocal, put that in front, so negative 1/2. And then we just clean up. So 5 times 1/5 is 1. So we end up with x to the power 5. And then negative 4 times negative 1/2 is positive 2. So we end up with plus 2 times x to the negative 2. And then our plus c. So really, this is the kind of the realistic amount of work that you'll be doing for these. And the nice thing with integration is you can always check your answer. So how do you do that? Well, let's take our answer right here, and we're going to differentiate it. So we're going to differentiate that. So what happens when we differentiate x to the power 5? We get 5x to the power 4. What happens when we differentiate 2x to the negative 2? We get negative 4x to the negative 3. And then what happens to a constant that's added on at the end? Well, the derivative of a constant is 0. And if we wanted to, we could rewrite that negative exponent back as a fraction. So instead of x to the minus 3, we could write that as division by x cubed. And we see that this here is exactly what we started with. So that means we did everything correct. So you can always check your answer. If you take your answer and differentiate it, you should get back to where you started. All right. So next time, we're going to kind of look at just a few more examples where we see our integration tables. So we'll see a list of integrals that we should just have memorized, and that'll really kind of expand our kind of universe of what functions we can actually integrate. But we'll see that next time. All right, so we'll stop there. Have a nice weekend, and then for anyone in the Thursday recitation, we have our exam 5 today. And then just a reminder for next week, we're going to have our homework for learning outcomes 05 and 06 due on Tuesday and Thursday. And then the homework for integration will be available on WebWork for you to get started on that as well. All right, so let's stop there. Have a nice weekend, and we'll see everyone next week. Bye-bye.